the elements of M are all multiples of C. Okay. This means there is no need to write this line, but if you look at the proof and go through these lines, it will help you better understand the situation, because sometimes it may not come to your mind that what's happening, what is the big picture, what is the thing as a whole. Okay, it's very necessary and important to keep track of what we are doing. What is the larger picture? We should not get confused, and we should not concentrate on a single calculation all the time. I mean, once the calculation has been performed or carried out properly without any mistake, then you have to draw yourself back and you have to look at the situation. You have to see what the calculation is saying about the general thing. But what is the significance of the calculation in the general scheme of things? Otherwise, you will get lost inside a proof. Okay, so this means that's why this type of explanations are sometimes important to write. This means C divides every element of M. In particular, C divides A and C divides B because A belongs to M. Why? Because A can be written in this form. And B also belongs to M because B can be written in this form. 0 times A plus 1 times B. So we have shown that C divides A and B, and we have also shown in a much easier way in the beginning itself of the second paragraph that if something divides both A and B, then that divides C also. So C has all the requisite properties to be the greatest common divisor of A and B. Furthermore, C is positive. Okay, hence C is equal to A comma B, and the claim is proved. So this concludes the proof of this existence theorem. So the existence theorem is nice in the sense that it not only says that GCD exists, but it allows us to express GCD in a very nice form involving the given integers. Okay, now let's now look at the condition. If at least one of A or B is non-zero, if you recall the part of the proof that we have cleaned, we don't have it here right now. The proof starts by showing that M has at least one positive integer. So the fact that at least one of these two numbers is non-zero plays a role in that part of the proof in showing that M has at least one positive integer. What goes wrong if both of them are zero? See, the result that we have seen before this lemma, which says why it's called the greatest common divisor, that result justifies this situation if both the integers are zero. And if you think of it like this, that other example, there we wrote down the positive integers of both 60 and 24. We noticed which ones are common, and from among them we chose the greatest one, and the result allows us to say that that is the GCD. Here, however, there are infinitely many positive integers. It's because every positive integer, infinitely many divisors, because every positive integer divides 0, or every non-zero integer divides 0 more generally. Why? Because 0 can be written as 0 times k. So that's why k divides 0 for any non-zero integer k. So if we try to think of the positive divisors of 0, they are all the positive numbers. Like that, for this one also same. So although they all of them are common divisors, there is no greatest. So in this particular case, there is no GCD. But this is a very dull case and a singular case. So we don't bother about this. The interesting things are there when we have at least one of them to be non-zero. And there also the real interesting thing situation occurs when both of them are non-zero. Let's just quickly look at what happens if exactly one of them is 0 but the other is non-zero. Let's just look at that. Suppose you have two integers. Let me take a concrete example, 12 and 0. What is the GCD of this? You see, the divisors of 12 are of course what we already know, 2, 6, 3, 4. So these are the positive divisors of 12. And what about the positive divisors of 0? All of them, all the positive numbers. So that means all of these are common to the other numbers. Among them, what is the greatest one? 12. So 12 is the greatest common divisor. In other words, if you consider a non-zero integer k and 0, the GCD is nothing but mod k, because k can be negative also, right? And we insist that the GCD is positive. So this is settled, this case is settled. So we are more interested in the situations where both a and b are non-zero. And in one of the exercises, we will come across an algorithm which will help us uh, find out the GCD in some steps. Okay. Now, having gone through the existence and uniqueness of GCD, we are now ready to look at a very special but very important case of this concept, and that is coprimality or relative primality, and that goes like this. Yeah, that thing is just this. It's a new thing, not really new, but it comes from the concept of GCD. A and B are said to be relatively prime, or sometimes they are also called coprime to one another if their GCD is equal to 1. Okay, if in this special case we say that A and B are relatively prime or coprime. Now there is a corollary to lemma 131. This corollary again Herstein does not number. So corollary to lemma 131 that I am adding. So the inconvenience of referring to these results when later you need them is that you have to write by the corollary to lemma 131 instead of, say, for example, writing corollary 132, something like that. So you have to write more. But anyway, so the corollary says A and B are relatively prime if and only if one is equal to MA plus NB for some integers M and N. It's time to refill. Give me a moment. Okay, so now this result, one part of it is actually given in Herstein's book. He says that if they are relatively prime, then this happens. Whose proof is very easy, but the converse also is true, which is also easy to see why it's true. But anyway, I have decided to include it here itself, and let's now look at the proof. One part is almost trivial. First, assume that A and B are relatively prime. So this is the definition of relative primality, or should I say relative primeness. Anyway, what I say does not matter, the concept matters. Okay, then by lemma 131 we directly have 1 equal to MA plus NB for some integers M and N. Why? Because we have already shown in that lemma that the GCD is expressible as an integer combination of A and B. Now the GCD is 1, so 1 is expressible in that form. Now conversely, assume that 1 can be expressed in this form for some integers M and N. Okay. Now from the proof of lemma 131, you recall what we did in that proof. We had the set M. We first showed that the set has at least one positive element, so it has a least positive element, and that turned out to be the GCD of A and B. So from the proof of lemma 131, this is the smallest positive element of M. So since 1 equal to MA plus NB belongs to M, see, now 1 has the form to be inside M. So 1 belongs to M and A comma B is the smallest positive element. 1 is also positive. So from this we have, using that smallest nature, we can write this. Okay. But positivity of A comma B, because GCD by definition is a positive integer, and since 1 is the smallest positive integer, we also have A comma B is greater than or equal to 1. So using these two inequalities, we have equality by the anti-symmetry of order relation. Hence, the GCD of A and B is 1, that is A and B are relatively prime, and that's how we get the proof of this corollary. Okay, now we come to the ultra important concept of prime numbers. Now this is the central, it can be said to be the central concept of number theory, because of the fact that prime numbers are the building blocks for all positive integers. And if you think of, if you include negative integers, for negative integers also. And that fact comes from a result called the fundamental theorem of arithmetic, which we will prove here. The thing is that, as you already know, if you start with a positive integer greater than 1, then that can be decomposed as a product of smaller numbers, like this. Say 2 times 6. Okay. Now this decomposition process may go on. Just like when a biological organism dies, its parts are decomposed, okay, into smaller constituents. They further break down, and ultimately the elements go back to nature in various forms, matter, energy, etc. So this is also somewhat similar. So that's why the word decomposition is used. Now 6 can be further decomposed as 2 times 3. Okay. The sense here is similar to that one also. Breaking down the thing into its smaller parts, into its simpler constituents. So now, once we reach this stage, they cannot be further decomposed in a non-trivial manner. I mean, what can you do with 2? You can at most write 1 times 2. So this is the last stage where after this, everything we do is trivial and unnecessary. You can write many ones, multiply them, but nothing, no new numbers will appear. No new interesting numbers will appear. So once this stage is reached, we say that we have a prime factorization of 12. And these numbers, which cannot be further decomposed in this fashion without having trivial cases like this, they are called prime numbers. So in short, prime numbers are integers with no non-trivial factorization. So such an expression is said to be a factorization of an integer. Now for technical reasons, we do not include 1 among the prime numbers. It's because if we include 1 among the prime numbers, then in the fundamental theorem of arithmetic, uniqueness somehow is destabilized. I mean, it creates unnecessary problems. Okay, so because of that reason, 1 is not considered as a prime number. Prime numbers by definition can be negative also, and you already know what they are. these are the negative primes, these are the positive primes, numbers which have no non-trivial factorization. Now since introduction of a negative sign does not actually introduce or include any interesting cases or does not contribute anything new to the study of primality of an integer, or for example the factorization of an integer, so negative primes are left out. They are there, but they do not contribute anything new. They do not bring anything new to the table, so they are left out. And we define prime numbers as positive numbers. Okay, so the actual definition goes like this. The actual definition is just this. So again we come across a definition which is just a definition without any numbering. When it's about prime numbers, an integer, although I should not write integer, but for once let's just write an integer p greater than 1 is called a prime number, or by abuse of grammar, a prime. Although prime is an adjective, but we can use it as a noun. It's okay. Mathematics में चलता है. Or a prime if the only divisors of p are plus or minus 1 and plus or minus p. Note that although we are restricting the definition of prime numbers to the positive ones only, but divisors can be negative. In the definition of a divisor of an integer, since we are dealing with integers, we have not put any restriction on b. The only restriction is that b cannot be 0. B can be negative also. So in that sense we have devised this definition. Okay. Now definition is quite simple. The concepts of divisibility is simple, and the other properties associated with it. But let me digress a little bit from our usual discussion. But the appearance of the prime numbers on the number line is one of the biggest unsolved mysteries in mathematics. How they appear, how frequently they appear, where they appear, there are many unsolved problems in number theory regarding this. And although a lot has been uncovered by the number theorists, many more are still there. For example, there is one very famous problem. It's by far the most famous unsolved problem in mathematics. You may have heard about it, the Riemann hypothesis. It somehow is related to the distribution of prime numbers on the number line. It remains unsolved. Most mathematicians believe it to be true, but proof is far beyond anyone's capability at this point. People have tried to prove it in many ways, but they have failed so far. There is a $1 million prize on someone who can prove this hypothesis, settle this hypothesis, either prove it to be true or show that it's not true. So far, what mathematicians have seen suggests that it has to be true, but a formal proof is far beyond anyone's capability at this point. I'm not going to discuss what the statement of Riemann hypothesis, because it involves something called the Riemann zeta function and its analytic continuation. So those things we will discuss when we study complex analysis. Okay, that will also come at one point. But this is a fascinating subject, and it's here there that you come across many contributions of the great Srinivasa Ramanujan. Anyway, uh, putting those things aside, since we are getting way ahead of ourselves, let's just come back to art and ordinary mathematical art and continue with our discussion. Now, there are some very important lemmas which help us investigate the behavior of these prime numbers. So the first lemma is the one it's very useful. I think it's related to Euclid, or I don't remember. Anyway, the statement goes like this. Now this lemma is the second lemma in this section, so it's lemma 132. If A and B are relatively prime and A divides the product BC, so A, B and C are integers, and the fact that A is involved in this divisibility relation and A appears on the left hand side tells you that A is non-zero. Not just that, A and B are relatively prime and it's given that A divides the product BC, then A has to divide C. Okay, and the proof is not very difficult. Since A and B are relatively prime, from the corollary, see, this is where things are somewhat annoying. We have to write from the corollary to lemma 131. 1 is equal to MA plus NB for some integers M and N. Okay, so this we are getting from the previous corollary. Now you multiply both sides by C. Then C is equal to MCA plus N, let me write it like this, NBC. Since okay, so now look at this expression. We are concerned about whether we have to show that A divides C, not that A divides MCA, because it's a multiple of A. Since A divides MCA and A also divides NBC, and where is that coming from? Because it's given that A is dividing BC, so A will divide a multiple of BC, also NBC. We have A divides this sum by exercise 2, that we are not going to mention anymore. We have A divides MCA plus NBC, which is equal to C, and this completes the proof of this lemma. It's very important, and its importance is brought out by the following corollary, and the corollary goes like this. says the corollary has appeared exactly below this lemma. So it's a corollary to lemma 132. To lemma 132 I'm not going to write once more, okay? So if a prime number, I should write prime number, but since I have decided to abuse grammar and I may call it a prime also, so I choose the shorter one. If a prime divides the product of certain integers, then it divides at least one of the integers. This result, okay. Now this appears in the text as an exercise. Its proof is not given, but it's easy, and we will not solve it as an exercise, but we will provide the proof here itself. So just like exercise 1 and 2 have been solved, exercise 16 will be solved here in the form of a proof. Okay, and the proof will go by induction. We apply induction on the number of factors in the product. By the way, what does this result tell you? It tells you that if P is a prime number and it divides a product of some integers, say a1, a2, a3, etc. up to an, then P has to divide at least one of these AIs. So there will be some AI which P divides. This is what we want to show. This is what the statement asks us to show. And we will prove this by induction on n, that is the number of factors in this product. So we will prove the result when n is 1, and then we will follow the usual induction. Okay. If n, okay, since I don't have n or anything, if there is only one factor in the product, the result is obvious. Why? Because you see, if I have only one factor, a1, and I have to show that P divides at least one factor. Since a1 only is available, so P is already dividing a1, so P is dividing a1, so the result becomes trivial or obvious. Obvious, trivial, same thing in this context. Assume that the result is true for any product assume that the result is true for any product of n integers where n is some positive integer, or we can say natural numbers also. I mean, n is some natural number, but keeping in mind that Now natural numbers are positive integers. This is not Tau's book, okay, this is Herstein's book, where 0 is not a natural number. But to be safe, we write positive integers. N is some positive integer. Let P be a prime and a1, a2, etc. an plus 1 be integers such that P divides their product. an plus 1. Okay. Then P divides. Now this product can be written as a product of two integers. How? I can write it as a product of this and an plus 1. Okay. If P divide, okay, now two cases arise. Either P divides an plus 1 or P does not divide an plus 1. These are the two cases that can arise. As far as an plus 1 is concerned, the last factor, it's either divisible by P or not divisible by P. If